So this topic it's really interesting because it stops and makes us think about real life applications. We can't really just think about a world without friction. A world without friction, the laws that we currently abide by wouldn't exist. So when we think about friction, we think about surfaces. So I had these out on purpose just so you can see the differences. And again, all we have here is cork, like a wine cork, the material, and this is felt. You've seen felt before, and this is what I was talking about. You put underneath a couch when you're going to slide it, so you don't want to ruin the floor, and it slides easily, but not too easily. And then this is Teflon. All right, so I'm going to pass these around. You can take a look at the different surfaces. But Teflon specifically has a very low amount of friction on it. This is what you would use to move things if you need them to move, and you can move them very easily. And the other day I was talking about you wouldn't really put this underneath the pads on a couch because the couch would move too easily, right? You'd sit on the couch and it would slide, actually, if it was on like the tile floor, if this was on the bottom of it. So felt gives it enough grip without sliding, without being too difficult to slide, and then Teflon will make it really easy. So you can take a look at the three different surfaces just to take a look at the materials themselves. Okay, so felt, cork had the most friction, Teflon the second most, and not Teflon, felt the second most, and Teflon the third.
Is that what's on the bottom of the chairs?
Is that what?
Is that what's on the bottom?
I don't know about these chairs. I can tell you. Let me see. Yeah, it's probably Teflon materials. But when you touch the white surface, you're going to see it's pretty much the same as what's on the bottom. The only difference, though, is over time, if you look at the bottom of these chairs, the little, it's like a white disc on the bottom made of Teflon. It's kind of gotten grooves all over it. It's kind of gotten a rough bottom surface because it's been slid back and forth. So over time, what happens? The friction value increases, actually. And that's kind of interesting to think about. You start with these chairs when they're brand new, you can probably slide it across the floor nice and easy. But now over time, they start to wear down. Those little Teflon pads, those discs on the bottom of each of the legs of the chair. So the chairs are now higher probably friction value than they were when you originally got them. So friction is a function of two surfaces. That's something that's key today. We want to make sure we understand. It's two surfaces, not one. How can I have friction with one surface? Friction involves what?
Two objects together.
Yeah, contact. Remember contact forces versus field forces? Friction is one of our contact forces. So two materials that are contacting one another exhibit friction. So this table here in your hand, or the board in your hand. But you can never say the friction of my hand has a certain value. It doesn't make any sense. It needs to be against another surface. Maybe two hands, maybe something like, again, the vulcanized rubber of a hockey puck on ice. Whatever the materials are, you need two of them to get a value of your coefficient of friction. So that's what we're going to look at today, and then we're going to apply friction with forces at an angle. So we'll start first. The general definition of friction, it's simply a reactive force, and it opposes some applied force. Now, you're going to say, well, there's no applied force acting on this, yet there's definitely friction. It's not sliding left to right. It's not moving on its own. But inertia is what's keeping it still, really. An object's desire to stay here is keeping it there. Sure, if I apply a force, though, now, from the side like this, I push on the iPad. When I push on the iPad, friction pushes back. When I push this way, friction pushes back. I could have friction when it's moving, or I could have friction when it's not. Look, I'm pushing. I actually am, with very little force. It's like I'm pushing on the desk very lightly. The wheels are pushing back. The locking mechanism has friction between the mechanism itself and the wheel. That friction translates to friction in this direction. So although I'm pushing on this desk like this, right, and the wheels are all locked so they're not able to turn, technically I think of friction as pushing back. Okay, I'm pushing this way. Friction is a responsive or reactive force. So we say that it depends on two things. The normal force and the surfaces. It makes sense to think about the surfaces because those are actually what create the friction, right? The two different surfaces are what create friction. So it depends again on the surfaces, that's obvious. Why does it depend on the normal force, though? That's the question really here. Why does it depend on the normal force? Yeah, you have an idea?
More normal force, more friction.
Why would you say that? I agree, but why? How do you get more normal force?
The heavier an object is, the more.
Yeah, that's the key. Very good, Matei. The heavier an object is, think about this for a second. Draw yourself a free body diagram if you need to. Here's the object. Weight acts down. Normal force acts up. If these forces are in a state of equilibrium, they balance each other, right? So you want to push this desk, or here, make it even easier. What's up, Chris? That's right. You want to push this chair? Pretty easy, right? Now somebody comes over and sits on it, and you want to push the chair. Is it as easy? And you would say, oh, it's heavier, normally, right? That's what you would think. It's heavier. But it has nothing to do really with the heaviness of the object. It has to do with the friction between the object and the object and the surface it's on. So in this case, again, when I sit on this chair and then you try and push the chair, what's happening is you're increasing Fg, which is acting down. And since Fg is balanced by Fn, you're also increasing Fn. So when you sit on an object or you increase the weight of an object, what are you really doing? You're increasing the normal force itself. And it turns out that the normal force is what is used to calculate friction. And as Matei mentioned, the more normal force, the more friction. They are directly related. Okay, we're going to see that in a moment with an equation, but that's something you should really definitely jot down here. The more normal force, the more friction. On the picture on the right, why do you think I have this picture here? What is that indicating? And you see like a little close-up or a zoom in. Use your intuition. This one is pretty obvious. You should be able to answer this without even any physics knowledge. Why am I showing that? What do you think?
Is it to show that the two surfaces aren't actually flat?
Exactly. They're not really smooth. Like you think this desk is smooth by going like this, right? It does feel pretty smooth. I mean, even this surface is really smooth. This is actually much smoother because this is a surface that's probably been polished. And there's actually, it's kind of ridiculous, but there was a whole class I took in college on material science for engineering, and we did an entire section on surface quality, it's called. And you use a polishing machine to polish a surface down to be perfectly flat or have no friction almost. And if you look at that, I mean, think about something like a piece of metal that's really smooth. You think it's smooth, but at the microscopic level, you see all these ridges, and that's what you're seeing here. So when you want to push an object or slide an object, the reason you have that initial friction force is because these surfaces are not really smooth. The bottom of my iPad case is definitely not smooth. It's meant to grip, right? So it doesn't slide anywhere. So the table itself, you would think is smooth, but when you push on it, it's meant not to move. So that's what's happening here. There are these little peaks, right? And between those peaks, there's adhesion. Do you remember with chemistry, you have these electrostatic forces between molecules that are different? So adhesion is what keeps these things together. It kind of locks them together in a sense. That's why when you push on something, if an object has been, like I use the example of a couch because I always think about like if you move furniture. If a couch has been sitting there for like 2 years, it's hard to actually move it. Sometimes it's almost stuck to the floor, you'd say. And then once you move it, it's able to move easily, right? It's easily moved afterward. Because of the overcoming of this electrostatic force between those ridges on the bottom of the actual couch leg and the floor itself. And again, sometimes it actually does stick together because of that attractive force there. All right, we're going to talk about two types of friction. So this is from the lab. Can somebody explain this? This was the type of friction you discussed in the lab. What is static friction? What's the whole concept of static friction? And if you need to think back to the lab of what you were looking at, you had to measure the static friction between the object you pushed and the surface. How did you figure out that measurement? What did you do? Or like, what was it exactly? Give me something, John. Yeah.
So when you were using the simulation, you basically had to see how much force it took to start to get the object in motion in the different situations.
That's exactly it. Static friction is exactly that. It's the force necessary just to get it to move. Static means stationary. So this is talking about the amount of friction that's existing before it moves, the instant before it moves. As soon as it starts to move, we're going to have something in a moment we're going to call kinetic. Kinetic means motion, moving friction, kinetic friction. So this is static friction. And this concept is really important that you understand because it's going to help us with the problems later. So we're going to get to math problems in a moment, but I'm going to go through some theory real quick to show you. And I've already kind of talked about this. We could say that static friction ranges. It ranges from 0 all the way through what we call its maximum static friction force. And let me explain this. It looks a little bit confusing at first. Fs is just the force of static friction, I'm going to say for now. Fs max is the maximum static friction. So an easy example would be to take my laptop here. Okay? And this is better because there's little grips on the bottom. You push with a pound of force, it doesn't move. You push with 2 pounds of force, it doesn't move. You push with 3 pounds of force, it doesn't move. Every time I push with more force, what does friction push back with? More force. If I push with 1 pound, friction push back with 1 pound for it not to move. If I push with 5 pounds, friction pushes back with 5 pounds. So friction can take on many values. Isn't that what this represents? Isn't this a range of values? Think back to your algebra course. When you represented a range of numbers, you would put x in the middle, and you would say x is between 2 and 7. And it means the smallest number was 2, the largest value was 7. That's what's happening here. What's the friction with no force at all? What's the friction? 0. That's this end. I push with 1 Newton, it pushes back. I push with 2, I push with 3, I push with 4, until what happens? Eventually it will? It'll move, and that's when I've reached the maximum static friction allowable. So again, I push, and then it starts to move. Now it's kinetic friction. So the instant before it began to move, that's the amount of static friction it can hold up against. Or not hold up against, but it can deliver to resist motion. Okay? So the idea is that it's resisting motion, and then it begins to move. The instant before it resists motion, before it begins to move, we have Fs max. Okay, it can take on a range of values. So to contrast static friction, we have kinetic friction. And the word kinetic simply means motion. So if there's something moving, there's something moving around, we know that it's sliding. An object is in motion, the problem says. An object accelerates, the problem says. All of these involve kinetic friction. And again, this is with respect to the contact of surfaces in motion. Not just pushing against each other, but already in motion. Kinetic friction here when you rub your hands. Static friction if you're just pushing them against each other trying to. Okay, again, no motion for static, motion for kinetic. That's the easy way to remember. Now, earlier I talked about how it's harder to get an object moving than to keep it moving. And if you've ever had say you had a stack of boxes and you put them on like a hand truck's easy because you have a little wheel. Say you had, if you've ever moved a piece of furniture, and I feel like I've moved so much that I just have all these ideas about it moving. It's the easy way to represent friction because there's so much friction. You have these straps usually that are used to carry furniture, but sometimes you could also pull on them to move them a little bit. So the instant before you begin to move it, you're really pulling with a lot of force. But once an object is moving, it's actually pretty easy to keep it moving. And the reason for this is that the static friction force that an object can feel from two surfaces is greater than kinetic. Static is greater than kinetic. So we could say that the force of friction that's kinetic is less than or equal to the force of friction that is static. Again, write this down if this is not clear, or you just look at this later in your notes. It takes more force to get something moving than it does to keep it moving, which is why static is more than kinetic, or kinetic is less than static. Again, it takes more force to get something moving than it does to keep it moving once it's already moving. And we're assuming at a constant velocity, which is fine, but either way, it's still going to be less for kinetic friction always. Matei?
So what if it's equal?
It can be. And some objects between two surfaces can have very close coefficients of friction between static and kinetic. And that can happen sometimes. But it's never going to be the other way around. You will never ever have kinetic friction being greater than static friction. It's just simply less than or equal to. Okay? And it just depends on the surfaces, so there's no one answer to that. But several surfaces that are in contact can have pretty much the same kinetic and static because they're so smooth. These are like things like a hockey puck and ice. That's what I mean for those. Okay? But anything with a lot of roughness to it will always have more static than kinetic because the roughness of two surfaces increases static a lot more than kinetic. Because remember I was talking about the electrostatic force between those little ridges, that adhesion. That adhesion is really what's helping in static friction, not as much in kinetic. Once an object is moving, adhesion isn't really slowing it down much. Adhesion is when those two things are in contact for a while, they start to stick to each other. They actually start to bond in a sense, not chemical bonds. Bond isn't like glue bonds to a surface. So with that said, let's take a quick look at our formula, and we're going to look at what this concept of coefficient has meant the whole time. So here's our formula. Ff stands for the force of friction. Fn, you know, that's the normal force. This other symbol is pronounced mu. It's spelled, if you were to write the spelling, like delta is spelled D-E-L-T-A, this is spelled M-U, mu. Okay? Simply put, mu is a rating. It's a rating between two surfaces. So if I have ice and metal, it's going to be very smooth, easy to move, low mu. If I have concrete outside, the sidewalk, and I'm dragging wood, there's going to be a lot of friction, right? That's a high mu value. So mu is a rating of the actual amount of friction between the surfaces. It's a rating. The higher the mu, the rougher the surfaces. The lower the mu, the smoother the surfaces. Okay? So you could say that the force of friction is directly related to mu. It's directly related to mu. The higher the mu, the higher the friction. The lower the mu, the lower the friction. And you can see that with the formula here. If you double mu, your answer for FF will double also because it's a product. It's multiplication. So the more mu, the more friction. It's a rating of two surfaces. Right.
So does that mean like the surface area would have an effect on how much friction?
Believe it or not, this is crazy to imagine. I know you're not going to believe me. Surface area doesn't theoretically affect friction. Now, you're going to say that's not possible. I've definitely moved stuff. And if it's this way versus this way, it's different. And you're right. That's because of what's called, it's like moment of inertia, actually. The reason that if you change the surface area in contact, it feels like you're pulling on something differently, is because of the tendency of the top of the object to want to topple or not. It's not the friction, believe it or not. It's not a function of the surface area. Which you would think it is, for sure, but clearly there's no surface area in the formula itself. Mu is only a material property. So, for example, mu between wood and concrete. You can look that up in a table. The mu value between ice and metal. You can look up in a table. The mu value between Teflon and granite. You can look that up in a table. These are values that are determined experimentally and published in tables. We actually, in part of the lab that we didn't get a chance to get to, what we would have been doing is this. We'd be calculating mu for these surfaces. You could actually calculate it yourself. And we're going to see today how to solve for mu in this, and I'll explain how that would have been applied. You could literally just hook up a force sensor, pull on this with enough force to make it move in a constant motion, and using math, you can determine the mu value of the volume of these. So that's what this lab that we're going to get to is really about, is determining mu of all three of these. What I may do is I may go over the lab in the next period, talk about it, and then just send you what the lab looks like so you can visualize a solution of it. So you can see, at least for the test, you can use that to help you study for it. Because we're really not going to have time to get to this other lab that I wanted to do. Yeah.
How much of it is conceptual?
I'd say, I don't make your tests until we're going to have them, but I'd say a decent amount would be conceptual. This is where a lot of the math is going to come from, this section and 5.2. We had some basic math in 5.2. We're going to have a little more complicated math here. Okay, so I'd probably say it's going to be around the same, 35, 30 in percentages, as the usual. Something else to recognize. Solve for mu, please. Solve the formula for mu. What does it become? Solve for mu. It should be quick. It should be instantaneous, your answer. George.
Over Fn.
FF over Fn. You just divide both sides by Fn. So a force over a force. What are the units of a force? Newtons over? What happens? So what are the units of mu? What are the units? There are none. Mu is unitless. Mu is unitless. It has no dimensions. It's not like newtons or meters per second or seconds. Mu has no dimensions. It is unitless. Jot that down so you know that. You're never going to get units from mu. So with that said, we're going to jump right into some math. And from this point on, we're really going to go through, I think, about 2 or 3 problems with math. We're going to look at something where a force is applied at an angle, then another 2 or 3 problems, and that's kind of the lesson for today. But it's going to take us a little while to go through these problems, so try to make sure that you're focused the whole time. After we do the first one, you'll see that there's a trend. You're going to approach these problems the same way every single time. Okay, it's actually, I think, a whole lot easier than projectile motion. It looks similar because we're going to make an x and y table again, but the actual motion and the equations are so much easier because we're always going to have the same equation. The equation that we're going to use for all of these problems is going to be this. Okay, our governing equation. This is Newton's second law. The sum of the forces acting is equal to mass times acceleration. We're going to use this formula in the x direction and in the y direction today. In the last class, everything we did was vertically acting vertically. So everything was in the y direction. Now we're in both. But remember, in order to come up with equations, you need a diagram here. So, I don't think we talked about this. No, we didn't yesterday. I didn't have you guys yesterday. It was 2 days ago. So, if we think about this, The actual diagram is what gives us the equation. So if we want to write down steps, I know some of you like steps. For all these problems, the steps are the same. So step one, draw your diagram. Draw your diagram. On the diagram, list your givens. You don't have to write the givens separately because they're going to be on the diagram. So draw a diagram with givens. That's step one. Step two could be recognize what you're looking for, meaning the desired variable. Are you looking for mu? Are you looking for Fn? Are you looking for Ff? Are you looking for the applied force necessary? What are you looking for? So diagram with your givens on the diagram, and then what are you looking for? And then go right into F equals ma in both x and y direction. Again, third step, use F equals ma in both the x and y direction. So step one is your diagram. Step two is list what you're looking for. Step three is use F equals ma in both directions. If you use this approach every time, seriously, you're not going to have a problem with these. It's the diagram that's important. If you have the right diagram, your equation almost can never be wrong, provided you're able to just literally copy from a diagram to the equation. That's all you have to do. So the diagram is what's the most important part here. Okay. So we have a 24 kilogram crate. It's at rest on a horizontal floor, and it requires a 75 Newton horizontal force to set it in motion. Find the coefficient of static friction. Why is this static friction in this problem? Right away, why is it static we're looking for and not kinetic? Why is it static and not kinetic, right?
It's because it's what to get the start moving.
Yeah. Look, find the coefficient of static friction if 75 newtons is needed to set it in motion. That means just to get it moving. This object is not already moving. There's not motion that's involved to start the problem. The problem says, what is the coefficient of friction if it takes 75 newtons just to get it moving? Now, I can ask a follow-up to this and say, what is the coefficient of kinetic friction if it takes 70 newtons to keep it moving? That would be kinetic friction I'd be looking for there. And again, it's always going to take more force to get it moving than it takes to keep it moving. So it takes me 75 newtons just to get it to budge. After that, 65 newtons. Not too bad. So you might be given two values of a force. One to get it moving, that'll give you static friction. And one to keep it moving, that'll give you kinetic friction. And you'll see that those mu values are different from one another because it takes more or less force to keep it moving than it does to get it moving. So we want to draw our diagram first. When we draw our diagram, I've been drawing boxes even though I said we can use a dot. The reason I draw boxes is for the location of friction so you can physically visualize. So if I'm pushing on this object, let's say I'm pushing it to the right. Okay, I'm pushing it to the right. I can draw that I can draw that arrow there, or I can draw it on the other side and say I'm pulling it. So here's the object in the middle of the room. I can pull it like this. So you'd show an arrow on the right side, or I can go like this, and I can push it. Does it say whether I push or pull? No. So does it matter? No. And honestly, mathematically, does it matter? No. All that matters is the arrow faces which direction in this case. Could you have drawn it to the left? Sure. But then which way would friction act? The opposite way. All that matters is that they're opposites of one another. So if this is the force that you're applying, then friction pushes back. Okay? Why the S? Why did I write FFS? What does the S stand for? Static. I'm specifying that I'm looking for static friction. And remember, this problem is not asking us to find the force of friction. It says find the coefficient. So we need that mu value. We're going to find that little symbol mu. We're going to solve for that. This is literally what we'd be doing in the lab. I'd be showing you, okay, let's use a force meter. We'll pull, we'll pull, we'll pull. As soon as it starts to move, we'll stop. And the force meter, as soon as it detects motion, you'll see a spike in acceleration. So what we'd see is there'd be more force, more force, more force, and then you'd keep it moving. So let me show you a graph of this. This is going to be, let's see, applied force is going to keep increasing, until it reaches that max, and then it's going to dip down like this. This is going to be a function of time. That's what it would look like. I'm pushing, it's not moving. As soon as it begins to move, I'm at that peak right there. This is 75. Again, it takes me 75 newtons to get it to move. So until I get to 75, I'm increasing force, I'm pushing harder, and then finally it moves, and now it's less force to move it. So you see that the force needed is a little bit lower, and it's about a constant force. It's going to vary, so even though my line was shaky there, that's fine that it is. Okay, that's what a graph is going to look like of this described motion. All right, that's a side note, just to keep on the side there. Anyhow, what else do we have acting on this object? So we've drawn the horizontal forces acting on it. Jake? Yeah, what do you got, Jake? And what else, Jake? Good. Okay, the normal force acting from the surface upward. Again, why isn't this crate falling to the ground? Because the ground pushes back up. The ground is Fn. The ground is Fn. Yes?
Fn and Fg are basically given in each problem, right?
Yeah, Fg is almost always given. If you have the mass, you have Fg, right? M times G gives you Fg. And then Fn is usually balanced with Fg. See how they're usually balanced there? We're going to see later with an example when they're not balanced, and we'll have to do a little bit differently there. Keep that in mind. So we've got our diagram. We can calculate Fg. Fg is a number. Remember, Fg is mass times gravity. Mass is 24 times 9.81. 24 times 9.81. I don't have numbers written down for these intermediate steps because I solved them all with variables. So if you could tell me what that number is, I can write that down next to our gravitational force.
235.44.
235 point? Thank you. Bless you. Okay, that's the weight of the object right there in blue. 235.44. How did Caroline calculate that? Again, mass times 9.81. Whenever you want the weight of an object, mass times 9.81. It's on your formula sheet. Your formula sheet says Fg equals mg, mass times 9.81. All right, so we have our diagram. What are we looking for? What are we looking for? What's our unknown? Static what? Close. I need more specific language. Not static friction. What am I looking for? What is it? Mu, the coefficient of static friction. It's different. Static friction is FFS. We are looking for this, mu s. Okay, we are looking for mu s. What is the coefficient of static friction? This is that value that relates to two surfaces that are in contact with one another. In the x direction and the y direction, we're going to have equations. We're always going to use the governing equation at the top. Now, in the x direction, what forces are acting? What's acting to the left? What's acting to the right? What's acting to the left? What's acting to the right? And you can't mess this up if your diagram's right. If your diagram's correct, all you got to do is literally read off what's acting either way. So what pushes it, Deirdre, what pushes it to the right in this case? What pushes it that way?
75.
And what pushes back against that? It's not a value in this case.
Would be the final.
What do we have? FF.
FFS.
FFS. What does FFS stand for again?
It's static friction.
Static friction force. So when I push the object this way, friction pushes back. So 75 is my positive force, FP. FFS pushes back against it. The force of friction that is static. And that equals MA in the x direction. Now, John had told us earlier that when we're dealing with static friction, we're looking for the force needed the instant it just starts to move. Or the instant when it's between moving and not moving, right? Or not moving and moving. So we're not going to say there's any acceleration because it really hasn't started moving yet. Remember, look at the graph. This peak here is when it just starts to move. After that peak, it's going to move. So we know that there is really no motion in the x direction. So if there's no motion, there's no what? Acceleration. You need to have that down. I keep saying that, and some people are still looking at me. Okay, you got to actually know that here. When there's no motion, there's no acceleration. So we don't have to worry about the right-hand side of the equation at all. Some of you are yawning. If you are, that's okay. But please go get a drink of water and come back if you need something. Take like a 2-second break if you need to. It's fine. Okay? If you find yourself doing that, please do that. I'd rather you get up and walk and then come back. In the y direction here, what forces do we have acting in the y direction? What do we got? What's that again?
Would it be Fn minus Fg equals 0?
Good. Fn is acting up, minus off Fg, and that's going to equal may, but he said 0 already, which he's right about, because there's no vertical motion at all. There's no vertical motion in this problem at all. Again, this is the weight of the object, so I'm putting 235.44 in, but in case you're wondering what it is here, this is Fg right here. And this 75 was the push that you applied earlier, Fp. I'm putting in the numbers to make life easier for you whenever we know the numbers themselves. Yeah, Ernest?
So then wouldn't Fn equal 235?
Exactly. Look at the right side. Everybody, look at this right here in the y direction. Fg, 235.44, is negative. How do I move it over? I add it over. So Fn is just 235.44. This is what Matei was mentioning earlier, how Fn and Fg are usually balanced. Usually. We're going to see when they're not in like 2 examples from now. Okay? So again, usually Fn is balanced with Fg, so we have 235.4 newtons. That's Fn. Where is that going to play a role? This problem doesn't say find Fn. Nowhere does it say find Fn, so that's a waste. I just did that for no reason. I don't know. It's wasting my time. Where do you think it's going to play a role? Where? Physically, where in the arrangement of the problem? Ernest, what do you think?
Isn't that going to be the linking variable?
Very good, Ernest. Well done.
It is,
Why? Where else does it appear?
and the formula for mu, since it's FF divided by...
Yeah, replace FF with its formula. What's the formula for FF from the previous slide? Go back up. What was the formula for FF? What do you got, Nick?
F equals
Mu, go ahead.
Fn.
Mu Fn. So replace this with mu Fn, and then you're going to put Fn in. Again, let's see this. This is just like the the projectile motion, where time was the linking variable. Remember, you took time from the y direction and moved it over to the x direction, or vice versa? Here we've got this. 75 minus mu times Fn. Remember, mu Fn is the formula for friction. And we're trying to find mu. So take Fn from the y direction and plug it in right here. Good job, Ernest. Way to see that. We take this value right here, 235.4 newtons, and plug it in right there for Fn. And then solve for mu. So I wasn't joking when I said it's kind of easier than projectiles, because we're always going to use the same equations. They're just going to change depending upon how many forces are acting on the object. Okay, so I would add the mu 235 over and then divide by 235. So I'd add it over to the right-hand side and then get mu by dividing. I'm going through all these steps on purpose right now because I want to make sure we all get this, but I'm going to really go through them much faster next time with the math stuff. I'm not always going to solve this, so please make sure you understand what we're doing here. I move this whole term over, mu s 235 by adding, and then I divide by 235. It's going to be a fraction, obviously, here. What do we get?
I didn't get a fraction or a decimal.
Decimal, sorry, meaning a number less than 1. 0.318. 0.318. What are the units? Good. Don't fall into that trap. There are no units. Remember, mu has no units. So this is what's called the coefficient of static friction between what? Between the crate that we're moving and the floor. We're not even given materials here. We don't know what they are. But you know what you could do? I could give you a table of mu values, and you could figure out actually what the materials are, or most likely. If you know the crate is wood, look for wood on other materials, and when wood on another material has a mu value of around 0.3, that's most likely what the other material is, or at least that same surface quality and rating. Okay? Questions on the first problem. This is the beginning of this entire section. It is the first problem we've done in this section with x and y direction. But notice again, the equations are the same. Look at the beginning. Go back to the beginning if you have to. At the very top up here, if you need to circle this, do it. This is the governing equation, F equals ma. And at that point, all I have to do is plug in from my diagram all the forces in the x for the x direction equals ma. All the forces in the y for the y direction equal ma. And then just progress through the problem. Okay, and then just progress right through the problem.
This is how,
Yes?
that's squiggly, that means, difference or,
This right here, this guy?
no. Top.
Squiggly thing? That means sum. The sum of. Another word for the sum of, meaning to add them together, is to say the net force. You could say net force equals ma. You could say the sum of the forces equals ma. Those are interchangeable statements. The net means sum. If you look at the net money you make, you take the positive money, you take the money you lost that year, the negative money, you get your net income, right? Or the money you paid to taxes, whatever it is. Net is to do with sum here in forces. Okay? Ryan, do me a favor. Can you open that window? All right, let's take a second example. I would like you to do the beginning. I want you to try, please, drawing a diagram, listing what you know in the diagram. If it gets really cold, you can close it. I just want some air flowing. And then what I want you to do after that is to consider what are you actually looking for here. Okay? So start this problem like the last one. If you want to check or talk to the person next to you, if you want to confer with them, but try it yourself for maybe like 10, 20 seconds and then confer with one another. Try to just draw yourself a diagram of what's actually happening. Do you notice anything interesting right away? What do you notice that's interesting right away? Deirdre, what do you
I
notice?
have a question. Would
Aye.
you say?
You have the right idea, but why did you draw their name? What does it say? Scroll by, huh? What does it say? Metaphors? Yeah, so make sure it's horizontal. It's got to be flat when you see that word. What do you notice?
There's an acceleration.
There's an acceleration in this problem. You're not going to draw that as a force. The way I draw that, I'm going to draw my force diagram, but I draw a little dashed line, and I write A equals, and I'll put my acceleration right there in the diagram. I always draw that just to show that it's moving. Okay, it's with a horizontal force, so it must be moving which way? Horizontally. Okay, so this is really AX. Again, it can't move vertically if there's no vertical force, right? There's no external force acting vertically. It's not going to move up and down. It's only going to move left to right. But what's the other thing you notice? I thought somebody else was going to answer with another answer here. What's the other thing that you notice now? There should be something, Gabe.
Well, now you have the mass of the box.
You're going to involve the mass of the box this time. It's not going to drop off anymore. You're not going to have MA dropping off to 0. Good. What else? George?
It's already moving. So
It's already moving.
So the static friction. Is there going to be no static friction?
So what friction are we looking at now?
Kinetic.
Kinetic. It's already moving. This problem involves motion already. We're looking for kinetic, and it says, determine the coefficient of kinetic friction. What else do you notice? I notice something else still. Try to see if you pick up on it. After you've drawn your diagram, look at your diagram alone, please. Look at your diagram. Do you notice something about it?
Is it that it's being pulled, not pushed?
Okay, it's being pulled and not pushed. But aside from that, Lauren, do you notice? What else?
Nothing in the y direction.
Oh, we do. Be careful. You have gravity. It's not shown. It's not an external. But you have gravity in normal force. Something else. Something else.
It's not.
No. The second thing to notice is this. It's the exact same free body diagram as the last one. It's absolutely identical. Whether I push or pull it, I'm pushing to the right. Friction is pushing back. I've got gravity down. I've got normal force up. It's the exact same free body diagram. It's absolutely identical. It's not always the same. It depends on the scenario. If I have two people now pushing against each other, I have a force pushing in either direction. Right? That'd be different. take a quick break, get some water, stretch your legs. We'll come back and look at this problem. I'll draw our free body diagram before you get back so you can see. I encourage you all to get up and move your legs, please. So let's use our equations of motion. Remember, here's the governing equation at the top in big letters. There it is. Every time we're going to have the exact same governing equation. We use that governing equation, F equals ma, in both directions now. In the x direction, what forces act in the x direction? Just list them again. It should be the same as last time because the free body diagram is the same as last time, right? So it's not going to change at all here. What do you got, Will?
So 55 minus is acceleration
Equals what?
equals
MAX, mass times acceleration. I'm not going to set this equal to 0 because there is acceleration in the x direction in this problem. In the y direction, it's the exact same equation as the last problem, literally identical. Fn is acting up, Fg is acting down, and that equals may, which is indeed 0 here. There's no vertical motion, there's only horizontal motion. So again, please recognize these are not any different from the last example because the diagram is not different. I made sure to do that on purpose here so that you guys can see that the diagram dictates the equations. The diagram is what gives you the equations. Same diagram as the last problem, same equations as the last problem. Only difference is that max doesn't drop off here because now we have acceleration because there is motion. But everything else is the same. Yeah, it's kinetic instead of static. Whatever, it's still the same. It's still friction. So we replace what we know. FF. What's the formula for FF again? This is one that you're going to have to know by the test. So I know you only learned it today, but it'll be on your formula sheet. So you just recognize how to use it. What is it? FF equals mu Fn. What kind of mu is this? What subscript should I put for the mu? K for kinetic. And that equals the mass, which is 8, times the acceleration, which is positive 1.2. In the y direction, I've got Fn equals 78.5 again. And by again, I mean again it equals the weight, not the number 78.5. So look at the y direction. If I have a 0 on the right-hand side, I simply add 78.5 over, and that gives me Fn. And now look at the x direction. Again, what's your linking variable in this problem? What is it? Fn. It's going to always be the linking variable. Plug in 78.5 there as a coefficient. This takes a little algebraic manipulation here to solve. So just be careful with what you're doing. We got 9.6, right? Because 96. I was thinking the same thing. 96 for 8 times 12. Yeah.
Those 3 places, like
For mu, I would go 3 places here because it's actually a very precise value based on materials. So a difference in mu on like the scale of 100 can actually have a difference on the actual material itself. So keep 3 places for this. When I keep 3 places, I'm getting 0.578.
yeah.
Check yours, please. I'm getting 0.578. Thank you. In a moment, I'm going to do one of these examples where I don't plug in numbers. Where we do everything with variables until the last step, and then we plug in numbers. See how earlier I'm plugging in all these numbers that we know? We know Fg, we know mass, we know A. I'm not going to plug in later, and we're going to solve everything what's called algebraically. If you prefer to plug in, and I'm doing that with that example, which I'm going to do in probably like 2 more examples, please, on your own, just stop and plug in the beginning and continue to solve. Okay, and continue to solve. Let me quickly pop up this animation of the simulation. If you want to, while you're waiting, actually, let's see. Do I want you to even? No. Wait for a second. Wait for a moment, because I'm going to go over a new topic in this section.
So we're going to go over the second part of the example. It's asked, like,
Yes, thank you, Ernest. That's a good part. What does the second part say?
how would the problem change if we're moving at a constant velocity?
Okay. The second part of the problem, how would it change if moving at a constant velocity? Constant velocity means what? In general.
Oh.
Constant, doesn't left or right. Constant velocity means
There's no acceleration.
no acceleration. So what does it change? How does it change?
There's acceleration.
Yeah, so this becomes 0. Everybody take a look if you need to. Again, if it were constant velocity, write this down because I'm going to give you a problem in the test, most likely, where it says an object is moving at a constant velocity. So you're finding mu k in that sense because it's moving, but there's no acceleration. So what would happen again is this would become 0 right here, which would make this number drop off, which would make this 9.6 simply become 0. Okay, it would change my answer. That's one of the reasons that I'm going to show you how to solve with all variables. Because if I suddenly say, oh, there's no acceleration, you could just find the variable in the equation and make it 0. Okay, so a generic solution is what I'm talking about. A generic solution. So we'll see that in the next example or two. Actually, I'll do that in the fourth example. I'll use a generic solution. So pause here for a second. That said, we're now going to go into this concept of, you know what? Most objects are not pushed at a perfect horizontal direction, or in a perfect horizontal direction. If I were standing here and pulling on this table, look where I'm pulling. I'm not pulling like this. I'm not getting horizontal and pulling. Most of the time, things are acting at angles. When things act at an angle, we need to break it into its components. This is where we come up with the concept of cosine and sine for the x and the y direction. This is analogous to what we did with velocities. So here's what I'm talking about. Here's your object. Imagine there's a force applied like this. It means really that you're pulling to the right and you're pulling up. Okay, think of this object as a sled. That's the easiest example I give all the time. If you attach a rope to a sled and you pull on it, just sometimes the sled will kick up off the ground because you're kind of pulling it up, but it'll also move to the right. So pull on a sled like this with a rope. It lifts up off the ground in the front and it pulls forward. So a force applied upward into the right direction is exactly that. It's a force really up and to the right direction. So whenever we have a force at an angle, what we're going to do in this chapter or this section is we're going to take that force and break it into its components. And I don't have to go through the derivation of this because I already did it. We did this in section 4.1 and 4.2 where these values come from. Why is it cosine? Why is it sine? It had to do with trigonometry, with our adjacent and our opposite sides of the triangle. But those are the values that you need to recognize. And what this allows us to do is this. Instead of drawing this diagram with a force at an angle, I can draw it like this now, with two separate forces. So instead, again, I'm going to erase over here, just so you can see the difference. These are interchangeable. Take a look at the two diagrams, please. If I drew the diagram in red with simply a force F, if that force acts at an angle theta, let's put that angle in there so you can see it. That's the angle theta right there. If that force acts at an angle theta, instead of drawing the diagram in red, please draw it the way you see it in black. Why am I pushing you to do it this way? What do you think will happen if you draw it this way versus this way? Why is it easier to draw it like this? How have we been solving all of these problems? Think about the last two problems we just did. When we solved them, we looked in how many directions? How many directions did we look when we solved them? We had up, down, left, right. So we don't want something at an angle, two directions, let's say, vertical and horizontal. But we had two directions. We don't want something at an angle. What does this diagram do? What does this diagram do? What does it do? Just two people, the same two hands allowed. This is not a hard question. How does it go from this diagram to this diagram and make life easier? And make life easier. Nick, what do you think? Yeah, it puts it into the directions that we want. It puts it into the x direction and the y direction. In this case, up and to the right, we didn't include down and left, those other two directions, but those are x and y also. So the idea here is this. if you can take a force acting at an angle and always, literally, listen to me, always replace it with F cosine for the x and F sine for the y, you will have all of your forces acting either vertically or horizontally. You'll never have to worry about anything at an angle if you break it into components. I did this quickly in the video you watched last night. Remember with the tension with Tom Cruise? Did you see that? Did you see that picture, by the way? You see I got Tom Cruise's face on there? That took me way too much time to do that. So Tom Cruise was walking across that tightrope, and there was an angle in the rope. The rope was angled down in the middle, was sagging in the middle. We broke up the tension that was acting at an angle into two directions. It's the same thing here. Okay, it's the same thing. So let's look at an example. Two students are sliding a sofa at a constant speed across a wooden floor. Right away, highlight this, please. Constant speed. When you see that, what does that make you think automatically? Constant speed? No acceleration. Very good, Will. No acceleration. And we also have the mass at the top. We can highlight that if we need to, but that's the mass right there. All right, one student pulls with a force of 225 at an angle of 13 above the horizontal. Another student pushes with a force of 250 at an angle of 23 below the horizontal. What is the coefficient of kinetic friction between the sofa and the floor? Between the sofa and the floor. Anybody want to demonstrate what this would look like? What would it look like? You can stand up and just do it on where your desk is on the end. How would you represent a person pulling with a force of 225 at an angle of 13 degrees above the horizontal? What would that physically look like? Yeah, show me literally. Show me what it would look like again on the table. Again, 225 and 13 degrees above the horizontal. That's like 90 degrees. You're lifting up. That's 90 degrees. Fit straight up.
No. What do you?
Yeah, Caroline, show him. Show him, Caroline.
Yeah, Caroline.
That's still like 90 because you're pulling up.
You can just like make your arm like that.
Yeah, there you go. Because look, ready, watch. This is 90 degrees. This is 0 degrees. This is 45 degrees. Here's 13 degrees. So you're grabbing the desk and pulling like this. Okay? 13 degrees. Very good. That's that small angle. So, Matei, you were like this. Ready? This is 13. You were pulling at an angle like this, like almost 90, by pulling up. See my arm?
Because I thought it applied to the table.
Yeah, no.
Well, read what it says, though. Be nice. Read what it says. It says above the horizontal. So the table continues to be the horizontal. So let's draw this so we can see that one first. So here's the horizontal, and here's your force right there. And there's 13 degrees. We'll call this, in this case, F1, and we'll say that value is 225 newtons. So that's the first scenario. That's the easier version, actually. The next one is actually kind of complicated, and it's misleading. But I want to purposely go over this still. How do you push at 23 below the horizontal? How do you push? You want to demonstrate again? Use the desk if you want.
I just have a question.
Oh, yeah, go ahead.
Would it be like 67 degrees?
You could use the complement if you want to, and we'll see where that will play a role, but we're not going to use it in this case. But you could. It would just make it a little trickier to do that. 23 below. How would you push on an object? Wouldn't you push like this? Would you all agree it's like this? Is that how you push?
Would you do a negative?
So, yeah, we're going to have something to do with negative because you're like pushing down, right? So really, if I'm pushing like this, look, here's the horizontal right here. Here's the horizontal now. That's 23 degrees. So it's a little bit weird, but draw yourself a force pushing on this object, like that. And now your horizontal is here, and now you have 23 degrees. And that's a force of 250 newtons. So it's a little bit confusing. And again, if I make the horizontal in line with the top of the object, that's fine also. As long as you push down, that's the key. You're pushing on the object. Read what it says. Another student pushes with a force of 250 at an angle 23 below the horizontal. So I could draw that there. I could take this entire thing and slide it down a little bit. And put the horizontal here and the force acting like that. Again, it doesn't matter. I could draw it either way. So what I'm saying is this. I could also draw this diagram like this. Here's my horizontal and show the force like that and put 23 degrees and 250 newtons. But look at the diagrams. They would still have the exact same equations of motion. Even though I slid it down a little bit, this object would still be being pushed to the right and down. Again, the 250 newton force still pushes it to the right and down. Either way I look at this, it's pushing to the right and down. Okay, so it doesn't matter which way you draw that diagram. I'm going to erase the bottom one just for the sake of time real quick. Oh, no, I can't, of course. So I've got, again, this one here, and we've got this one here. Now, I don't want to draw my diagram like that because these forces act at an angle, and we know that when we do the math, we look at the x direction and we look at the y direction. Because we look at those two directions independently, I want everything in the x or everything in the y. So we need to break up these forces into their components. So I need you to think logically about what's happening. The force on the right is pulling in two directions. What two directions is this force pulling? What two directions? Up and to the right. This force,
Down.
down and to the right. So let's replace them. Let's draw ourselves a new diagram here. Let's draw to the right on both of them. This one is being pulled up, though, and this one is being pushed down. Take a look at those arrows, please, and make sense of them logically. Again, on the right side of this diagram, it's being pulled up and to the right. On the left side, it's being pushed down and to the right. But either way, both of these forces are to the right, but one is up and one is down. What other forces act on this object? What opposes motion? What opposes motion always? Friction. What pulls the object to the ground always? What keeps it on the ground always? Gravity. And what keeps it from falling through the ground? The floor. What do we call that force? Normal force. Okay, the normal force. Now, here's the first time you're going to see, Matei, this is to answer your question, where we really don't have the normal force equaling gravity. Because now you have these other vertical forces that are going to change it up a little bit, right? They're going to change the equations. I didn't label the vertical and horizontal forces in blue yet. Notice, look at the blue forces. I have not labeled them. Can somebody help me label them? Simply use the concept of F cosine theta and F sine theta for all of them. For all of them. Give me one of them. So which one do you want to point to? You want to do this one first? They're different values. Just give me numbers for them. I'm gonna put the numbers in their place for now. So this was the first force on this side. And that was the angle we used on this side.
So it would be 25.
225
times cosine.
of the angle.
13.
Good, that's that force. What's the force that's pulling upward? This is 225 cosine 13. Where does that come from? Please remember, guys, this was 225 and this was 13 degrees. So you literally take 225 cos 13 for the x component. What's the only difference between the x component and the y component? There's only one difference here. Sine. All you use is sine for that one. On the other side, please. On the other side. The numbers are going to change, but the concept is the same. Instead of 225, what was the force applied over here? How much force? 250. And what's the new angle, Gabe? 23. That's the only difference. So we've got 250 cos 23 now. And 250 sine 23. So this is really the same thing we did with velocities when we broke it into VIX and VIX and VIY. Okay, it's the same thing. X is cosine, Y is sine. X is cosine, Y is sine. If you don't remember this, you're not going to be able to do it on the test. You have to remember this. This is one of the times that I'm going to tell you, you need to remember to find cosine, to find the x component, multiply the velocity or the force in this case, by the cosine of the angle. Yeah?
How come for the normal force you kind of make it like a right angle?
It's always at a right angle. That's what, remember the word normal means perpendicular. I don't draw it on every diagram, but sometimes I just remind myself to draw that. How about the weight? What's the weight of the object? Mass times gravity. What do we got? 225, right? I don't have a number for it, actually. I never wrote it down. I did it all variables. 225 times 9.81, Ernest? What do you got?
2,207.25.
All right. So that's the weight right there. So it looks like we've defined all of our forces except for which two again? Which two forces don't we know the numbers for, just like last time? The same two forces are still missing. Yeah, FFK. Friction we don't know the value of, and the normal force we don't know the value of. Okay, those two things. This is moving with a constant velocity. We highlighted that earlier. And Will told us, when we see the word constant velocity, and I'm going to get rid of all that. Look at this. I can answer this question with nothing else. Literally nothing else. Okay, if we get rid of constant velocity, or we say it's constant velocity, it gets rid of acceleration. Okay, that's the other thing that we should know. Ax is 0. Constant velocity, no acceleration. And now we simply add and subtract. It's just going to get really messy. There's going to be a lot of numbers, but it's not hard. It really isn't. It's the same problem. How many forces act in the x direction? Look at your diagram. See how many arrows are acting left to right or right to left. How many is the question? How many? 3. What do you got? Read them off.
250 cosine 23, 225 cosine 13, and
Minus FFK. Okay, I agree. That's our x. That's our x direction. Does everybody see that?
Yeah.
Both objects or both people are pushing to the right, so those are both positive. Friction opposes motion. That is negative. In the y direction, we've got a bunch of forces. All you got to do is list them all. Go ahead.
225 sine 13.
Good. I'm going to actually run out of room, so hold on, actually. Give me 1 sec, Deirdre. Let me just do it over here. 225. Oh, I just moved the diagram, though. Here we go. Sine 13. Continue.
Fn.
Good. What's acting down now? You listed the two acting up.
250 sine 23.
Okay, and what else?
And
What pulls down on all objects?
2000.
Okay. The weight always pulls down, and that equals 0. We're kind of running out of room, so let me just make this a little bit smaller so we can see this all. All right, there we go. We've got everything on the screen, okay? So in the x direction, except for the diagram fell off again. In the x direction, we're going to see here that we've got 3 forces acting. In the y direction, we have 1, 2, 3, 4 forces acting. Look at the y direction. What can you solve for again? In the y direction, what can you solve for? What is it? Fn, the linking variable. Get Fn, replace FFK with mu Fn. Replace this with mu Fn to solve for mu. Okay, again, it's not difficult. It's all about organization. Notice it? Okay, if you're organized and you go through the process with the diagram with your correct arrows everywhere, it will make sense. So replace FFK right here with mu Fn. It's going to be a whole ton of numbers going on here. So it's just going to be really messy. Oops. Okay, yeah, it's kind of all out of whack here, but you guys can see what I'm doing. Solve for mu k by plugging in the number you get for Fn in the y direction. Fn in the y direction will turn out to be 2254.3. Take that, plug it in right there. That's what I got at least. I hope it's right. I have 2254.3. Yeah.
How did you get the F to G?
How did I get the FG? Mass times 9.81. Always. That's the formula for FG.
What'd you do to get the 20?
So right here's what I did. Take a look, please. I got a number from this, 2207, move it over by adding. A number from this, move it over by adding. A number from this, move it over by subtracting. So add these two to the right-hand side, and then subtract this quantity. You'll get 2254.3. What did you get?
I got 2386.
So you made a mistake somewhere. That's not a rounding error, so just check.
Yeah.
Okay? Just check. But again, the concept here is that we add things over to isolate one variable, take that variable, move it over over here for Fn to solve for mu. Mu will turn out to be 0.199. 0.199. 0.2, just so you know, just to give you an idea, 0.2 is rated as metal on wood. So imagine a piece of metal sliding on wood. But again, what is metal and what is wood? It depends on the material, right? What kind of wood. But metal on wood is a mu value of around 0.2. If you were looking at this for a couch, you were thinking a couch, this would be, you know those Teflon pads I said that would make the couch slide too easily? This is as if you put those on all four legs so you could just move the furniture maybe down the hall. It would slide very easily. This is a very low value of kinetic friction. Jake?
Is real friction gonna be on that?
Is what?
Real friction?
Rolling, yeah. At the very end of this lesson, I'm going to talk about rolling, but it's not going to be any mathematical at all. It's all going to be just conceptual, what rolling. And we talked about it quickly in here already, the concept, but I'm going to go over it again, yeah. Gabe, go for it.
So kinetic friction is the same as, like where it's like K.
It's the same formula whether it's kinetic or static, yeah. Except see here, this is a K for kinetic. If it were static friction, it's an S for static. It's always going to be mu times Fn. It's always going to be mu times Fn. Nick, you look confused. Ask.
No, my answers.
What'd you get, Nick?
2,000 greater than 4.3.
I mean, I can look to check again, make sure we wrote everything down right. You did or did not get this?
In the other ones, like 2015 times 23 plus, and then negative UKFN.
You add that over here.
Like we had to multiply by FN, like plus FN.
Yeah, it's multiplied by Fn.
But when I like just added it instead of multiplying it, I had like the same number.
Okay, so maybe that's the mistake you made. Thank you, Juliet. That's a good point to make. Try to check, guys. Please try to check your numbers. Okay, I'm pretty positive these numbers are right. I've checked them several times, and I always do the math when I go through them. So check that you get them. I'm going to go on to the next problem now, okay? I need to get to the next problem. The next problem is actually really interesting because I'm going to show you how we don't need numbers actually at all. You don't need numbers to do these problems at all. You can do it all with variables, the whole thing. It's not ideal, but we can do it all, and I'm going to do the whole thing with variables. So we've got a student moving a box by attaching a rope to it and pulling with a force of 90 newtons at an angle of 30 degrees above the horizontal. Now, instead of calling those values, I can also do this. I can use variables, Fp and theta. So these are the exact same diagrams. The box has a mass of 20 kilograms. The coefficient of kinetic friction is 0.5. So I'm going to write these values on the right. Now, notice in this problem, we're not trying to find the coefficient. We're given the coefficient this time. The question instead says determine the acceleration. So look at this problem, please. On the right-hand side, we've got all of our numbers. On the left-hand side, we've got variables. Let's stick with the variables just for a little longer here and see what happens. If I draw my other forces acting, I've got gravity pulling down, I've got friction pushing back, and I've got the normal force pushing up. So do me a favor, please, and ignore what's in the top right for now, and just look at this diagram on the left. Now, the force being applied, Fp, how do I find its components? How am I able to replace it? I can replace it with the force pulling this way, and I can replace it with the force pulling this way. Those blue arrows could be used instead of that one black arrow at an angle. I can replace it with those two blue arrows showing the components. Ryan, how do I find what's the x component always?
90 cos 30.
So Fp cos theta, I agree. You're using the numbers, I'm using the variables. How do I find the y component? Instead of cosine for the y component, what would I be using? Sine. So again, it's the force itself, Fp, times the sine of theta. And now what I can do is this. I can erase everything that was going on here. And I can't erase any smaller, so I'm just going to Of course that happened. I can erase everything that was going on there and just show it like this. So again, what you see in blue here is me resolving this 90 cosine 30 and 90 sine 30. But I'm not putting in the numbers just for a little while, please. Trust me, for a little while. Okay, if you want to put in the numbers and you're used to that, and you think it might make it easier, please do that for yourself. But if you want to see the algebraic solution, at least watch along with this. So I've got my diagram on the left. My whole diagram is right here. I need to take this diagram and write my equations of motion. In the x direction, I've got the pull to the right, which is Fp cosine theta. Where am I getting that from? Right here. This was a number in the last problem. We wrote down a number. I'm just writing out variables. I've got friction pulling back, or pushing back if you like. And we know that equals ma. In the y direction, I've got gravity pulling down, the weight. I've got the normal force pulling up. And then I've got Fp sine theta pulling up also. And that equals ma. This ma is 0 because it's not floating off the surface. Again, if it helps to plug in numbers and you're really lost right now, plug in numbers. Don't even listen to me. Continue the problem on your own and solve for acceleration in the x direction. You can solve for acceleration here by, again, finding Fn, plugging Fn in here into this formula, and going through it. But I'm going to do everything with variables now. So this is Fp cosine theta minus mu k Fn equals max. Over here, this is mg plus Fn plus Fp sine theta equals 0. So all I'm doing is plugging in variables. The formula for FFK, the formula for Fg has been plugged in. On the right side, solve for Fn, please, by moving these two terms over. Replace that right here, and you solve for Ax. It's just going to be really messy. But the cool part is that your whole answer is variables. And then at the end, you can just plug in the numbers that were given.
So would you say, would you say in the y direction you're usually using f equals mg?
Traditionally, we have in the past, but we're seeing here that it's not. Because look, move mg over by adding it, right? Add mg over to the right-hand side, but then you have to subtract Fp sine theta. How do you get Fn, right? Look at this. To get Fn by itself, you got to add mg over and then subtract Fp sine theta. So it's not always going to be using mg, but traditionally you'll see mg involved in that problem.
And my second question,
Yeah.
do you consider Fp cosine theta the same as because it gives us 90 newtons, so is that kind of like interchangeable?
That's 90 cosine 30. That's what we're using there. Fp is 90, cosine theta is cosine 30. Theta is the angle of 30 degrees. Fp, they're up here. Take a look up here if you need to, okay? Fp is defined right here. That's Fp, and this is theta right here. Okay, they're in the diagram in the top right. So if you simply take this expression for Fn and replace it here in Fn, you could solve for Ax by taking this whole thing with Fn in place and dividing by m. It's just really messy. So this becomes, I'll write it all as one line. Replace Fn there. So replacing Fn, I'll show you with the different colors so you can see this. Okay, so when I replace Fn there, that's what goes in place for Fn. And then how do I get Ax by itself? Divide by mass. It's all variables, but it's the same thing you would do with numbers, actually. Divide by mass. And that's our answer for Ax. Again, I know these numbers. Fp is 90, theta is 30, mu is 0.5, m is the mass of the object, which was given as 20, thank you. G is 9.81, again here, Fp is 90, theta is 30, m in the denominator, again, is 20. All you do is plug in numbers at this point, and you'll get the mu value, or the, not mu value, the acceleration value in this case.
If you give us a question on the test where it's with variables, will you ask?
I'll always give you numbers, but what I'm saying is that if you want to solve with only variables, you could do it all this way and then plug in the numbers at the end. I find it to be an easier solution because I don't make mistakes with my numbers along the way. I find it easier to move variables and then at the end plug in the numbers. But you can do it either way, Caroline. Hey, here's what I need you to do tonight. Listen carefully.